This diagram illustrates what happens when we try to learn from an improvised tutorial. Unscripted instruction is essentially noise. It forces the viewer to parse chaotic information, which can block the learning process before it begins. This diagram illustrates the biological constraint of instructional design. Working memory can only process about 4 to 7 chunks of new data at once. If we push too much through simultaneously, as shown in the red overload box, learning stops. This animated blueprint demonstrates the expert blind spot. When an instructor knows a process perfectly, they often skip microsteps that seem obvious. For a beginner, those omitted instructions act like missing planks on a bridge, causing the learning process to fail. Effective teaching requires engineering a step-by-step assembly line for the user's brain. The goal is to remove all friction from the path, so working memory is reserved entirely for the task at hand. When we write instructions, getting the user an action to perform before telling them where to look causes disorientation. They have to hold the action in their working memory while scanning the interface to find the correct menu. This is known as inverted sequencing. The solution is a strict syntax. State the location first, then the action. Instead of saying, click Export in the File menu, say, in the File menu, click Export. Additionally, every step must be limited to exactly one action. This flowchart illustrates the action output rule. Every imperative command must yield a verifiable result. When a user executes a step on the left, they need to see a corresponding visual change on the right to know they have succeeded. Using this predictable syntax builds mental momentum. It prevents the user from wasting cognitive resources searching the screen, allowing them to focus entirely on the procedure. This diagram illustrates the modality effect. Forcing users to read text while scanning a complex interface causes split attention failure. We solve this by moving instructions to the spoken track. This leaves a clean interface, allowing the user to focus solely on the target element. This technique requires precise timing. If the spoken instruction and the on-screen action are out of sync by even 3 seconds, the user struggles to match what they hear with what they see, and comprehension drops. Try this now. Take a bloated, poorly sequenced instruction from one of your own guides and rewrite it into a clean, imperative command that starts with the location. Visual silence on screen is as important as the spoken script. Stripping away non-essential visual data ensures the user's focus stays exactly where the voiceover dictates. We also use the gateway principle to manage complexity. This means prerequisites must be cleared up front, and a user cannot begin the next action until the current one is verified. This flowchart evaluates instructional complexity. Decide whether to integrate, verbally present, or remove information to protect working memory. By following these divergent pathways, warnings are front-loaded onto a clear detour path, ensuring they never interrupt the core instructional flow. Aggressively isolating these edge cases protect the happy path. This ensures that the majority of users can complete the primary task without encountering unexpected friction. This layout demonstrates how these principles function as a single system. The script on the left drives the precise, synchronized interface actions on the right. The process begins by stating the location first, followed immediately by a single action verb. This maintains a strict 1-to-1 ratio between the instruction and the output. Elements are visually isolated while they are explained verbally, and all warnings are front-loaded to ensure the user is prepared before they encounter a risk. In instructional design, clarity serves a functional purpose. By following these structural rules, you ensure that the pace of your instruction always fits within the fixed capacity of the human brain.